Alright, the purpose of this video is to look at radicals. We'll mostly be simplifying doing operations, add, subtract, multiply, divide with radicals, but we'll also look and see that radicals can be expressed as fractional exponents. In other words, if I have the square root of 5, that's the same thing as 5 to the 1/2. So half is as an exponent. So those are the two things that we're going to be looking at so far. So square roots or radicals, by definition, you could say a number c is said to be an nth root of another number a if you take c and you raise it to that nth power and it's equal to a. Or in other words, you can say 9 is the square root of 81 if when you square 9 you get 81. Now, when you do the square root thing, maybe I'll go on this slide here. When you're simplifying, like this one, square root of 81, okay, we know that's 9. But there's lots of numbers that are, I like to call them perfect numbers, or ones that can be taken the square root of easily. Like if I take the square root of 1, that's 1. Square root of 4, that's 2. Square root of 9 is 3. 4 squared is 16, etc. So these numbers here I would call the pretty numbers or the perfect numbers because I can take the square root of them. If I take something like the square root of 18, that's not one of those perfect numbers. Maybe part of 18 is, and we'll look at that later, but the number 18 isn't one of those perfect numbers. Here, if you're taking the negative square root of 36, that would be negative 6. If, however, you're taking the square root of negative 36, you can't do that in the real number system. It doesn't work. So if taking the square root of negative, you can just say that's undefined. Now, if I was taking the cube root of a negative number, that would work, because for this particular one, if I took negative 2 and cubed it, I'd get negative 8. So in this particular case, this one does work. But if you're taking the square root of a negative number like this one, undefined, under the real numbers. Here's some rules that you can use with square roots or radicals. First one is if you're taking the nth root of a radical, but that the factor inside is being raised to that same exponent, then those basically cancel out. For example, if I take the square root of x squared, the square root and the squared sort of cancel each other, so the answer to that would be x. Or if I were taking the fourth root of, say, 16, that's the same thing as the fourth root of 2 to the fourth. The 4's cancel, so that would just be equal to 2. Okay. Same thing if the index is odd, you get that same rule. Also, if I'm taking the nth root of a value and I'm multiplying by the nth root of another value, I could just rewrite those all under one nth root. So if I have the square root of 6 times the square root of 3, that's the same thing as the square root of 6 times 3, or the square root of 18. Okay, when you're dividing quotients, same kind of rule. And lastly, if I'm taking the square root or the nth root of anything that has a power, I can write it like this, or I can just write it the nth root of a and then raise that whole thing to the mth power. So the m could be, that power could be inside the radical or it could be outside. Okay, so we can move those around. Okay, so let's look at a couple of those rules. Here's a square root of a square. Those two cancel, so my answer is just -7. Square root of a square, cancel, answer is x minus 5. This one, it's a product. Let's separate those. So it'd be the cube root of 27 times the cube root of x to the 12th. Cube root of 27 is actually 3, because 3 times 3 times 3 is 27. Cube root, so the answer to that would just be 3. This one here, let me see if I can simplify that. The 3 means I need to have 3 things that are the same inside, and I can take one out. I'll do this the long way. and just show you that x to the 12th means you've got 12 x's inside. Okay, how many is that? 6, 7, 8, 9, 10, 11, 12. Okay, so there's 12 inside. So for every 3 that are inside, I can take 1 out. There's 3. I bring 1 x out. There's already 3 out there. Another 3, I bring another one out, so that would be x. Another 3, another x. Last 3, another x. And then I've taken all the x's out, so there's nothing left in the square root. So my answer is just going to be 3 times these 4 x's, or 3x to the 4th. Another way you could have done that is just looked at this and said, well, cube root of x to the 12th is the same thing as x to the 4th cubed, right? Because 4 times 3 is 12. Now the 3 and the cube cancel, leaving me with just x to the 4th, which is what I had to begin with. Okay. Here's just another couple ones that you could do. Square root of 75 I could rewrite as a square root of 25 times 3. According to one of those rules, I can split that up now. So it's a square root of 25 times the square root of 3. Square root of 25, 25 is one of those perfect numbers, so this would be 5 root 3. I couldn't simplify root 3 anymore. Using a similar rule here, the 4th root of 768 times the 4th root of a to the 6th to the 4th. See how I got, so those were the same. And then the 4th root of b to the 4th. We'll do the easy stuff first. These cancel, leaving me with a b. These cancel, leaving me with an a to the 6th. And now 768. What'll divide into that? I just did this. 768. So it's a 4th root of, I guess 2 will go into that. That'd be 384. 2 times 384. 2 will go into that again. So 2 will go into that, 192. And then 2 goes into 192 as well. So 192 is 2 times, that would be 96 times 2. And then 2 times 2, 96 is 48 times 2 times 2. Hopefully I'm getting all my 2's there good. And then 48, is 16 times 3. So 2 times 2 times 16 times 3 times those other 2's I'm going to put up front here. 2 times 2. There. Now, if all of this is under the 4th root, right? So there's 4 2's, I can bring 1 out. 16 is 2 to the 4th, so I can bring another 2 out. If you rewrote 16, it'd be 2 times 2 times 2 times 2. And then there's a 3 stuck in there. So let's see, I bring 1 2, there's another 2 out, and then it'll still be the 4th root of 3 inside. Is that right? That seems odd to me. Something's funny. Anyway, and I have an a to the 6th b. So that would be 4, then the 4th root of 3 times a to the 6th b. So 4th root, so if I had to put that back in, it'd be 4 times 4 times 4 times 4. So it'd be 256 times 3. Yeah, that works out. Yeah, that's correct. Just notice how I was figuring out that. Like sometimes you can't just get it immediately with a calculator. Sometimes you have to do a bit of finagling. But always, if it's a 4th root, you need 4 things inside to bring 1 out. Okay, here's a couple other questions. They're doing basically the same thing. Maybe I'll just do this letter D just to show you that. So the 6th root of all of this stuff, I can separate that into the 6th root of x to the 18th, the 6th root of y to the 42, over the 6th root of 5 to the 6th. So here 6 and 6, these cancel. So on the bottom, for this one, I would have 5. And then here, x to the 18th is x cubed to the 6th. So I could take out an x cubed, be left with nothing inside. And then this one too, 6 times something, 7. So that, the y to the 42, I could write as y to the 7th to the 6th. And if I'm taking the 6th root of that, the 6's cancel, so it would just be y to the 7th. Okay, hopefully that's helping out with some of those. Here's some other ones, same kind of game with those. Let's take a look at adding, subtracting radicals. When you add and subtract radicals, you must have a common radical, and once you have a common radical, then you can add or subtract, but you only add or subtract the numbers out front. So here I've got a radical, here I've got another one. Each of them have a root 3, so I can add or subtract the first two numbers. So 2 plus 9 is 11, and I keep the, I keep the 3, or the radicand. Okay, I keep the 3 the same. Whoops. So it'll be 11 root 3. This one here, these aren't the same. And I can't make that one, change that one to be a 5 to make it the same. So I couldn't do anything with this. I would just have to leave it like that. Try a couple more. Let's try this one. Notice the radicands aren't the same, so I can't really do anything. But can I simplify that? Again, I'm looking for pretty numbers like 1, 4, 9, 16, 25, 36, etc. So do one of those numbers there divide evenly into 45? The 9 does. So I could rewrite this as 12 times the root of 9 times the root of 5. See how that one splits into that? 80, same thing. 80, I think it's 16 times 5. So it'd be root 16 times root 5. So now root of 9 is 3. 3 times 12 is 36. So this would be 36 root 5. Root of 16 is 4. 4 times 8 is 32 root 5. Now they're both root 5, so now I can gamble with their coefficients. 36 take away 32 is 4, so the answer to this would be 4 root 5. Similar kind of thing with that question. Okay, so that's adding. Now let's look at multiplying. When you're multiplying radicals, you want to think about sign, number, and letter, if there are any letters. But it's when you're multiplying this, it looks like I have a binomial here, a binomial there. So when I'm multiplying them, I have to do that whole FOIL thing, first, outer, inner, last. So you worry about the sign, the number, and letter if you need to. Okay, so multiplying this, positive times positive is positive. 2 times 1 out front here would be a 2. Root 3 times root 3 would be root 9. That's what I would get with that first product. Okay, now let's do the second one. So, let's do this one. Yeah, there we go. That one times that one. So root 3 times 1 would be a positive root 3. Okay, next one. 1 times 2 root 3 would be a positive 2 root 3. Okay, and then lastly, 1 times 1 would be a positive 1. So it's just foiling like you normally do, but you have to make sure that you are keeping track of the sign, the numbers, and also those radicals. Okay, square root of 9 is 3, so 3 times 2 is 6. Root 3, that's like 1 root 3, plus 2 root 3 would be 3 root 3. Notice I can't do anything with that number. When I add these, the root 3 stays the same, plus 1. Now 1 plus 6 I can add, that's 7, plus 3 root 3, done. With this one, if you're foiling that, make sure that it says squared, so that means I have 2 of those. So I have to do the same thing, FOIL, first, outer, inner, and last. Now one application of using square roots happens when you're using the Pythagorean theorem, where you have a hypotenuse and 2 legs and you have a right angle, and the relationship is you square one of the legs, add square the other leg, and that has to equal to the square of the hypotenuse. When you're solving for any one of these, typically you're going to have to take a square root. Here's an example of one. So I have a slow pitch diamond is a square, and it's 65 meters on a side. So all these sides here are 65. Okay, and the question is, how far is it from home to second base? So that distance right there. So if you look at that right there, if this is a square, here I've got a right triangle, where this is the hypotenuse, and each of these are a leg. So the formula is leg squared plus the other leg squared is equal to the hypotenuse squared. So here I have to go 65 squared plus 65 squared is equal to the hypotenuse squared. Okay, I need to bring in my trusty calculator here just a sec. Calculator. Okay, so 65 squared. Where'd my pen go? Whoops. Okay, let me clear that. So 65 squared, 4225, and I have two of those, right? So let's just times that by 2. So I have 8450, and now I have to take the square root of that, which is this button. So 91.9. So this distance across there is 92.9. Okay, 92. Oh, my pen's funny. Okay, my pen's back. So I think the answer was 92.9, right? So hypotenuse is equal to 92.9. Might have been 91.9. Yeah, whatever the calculator said. Okay, so, and the idea there was to solve for the hypotenuse, you had to take the square root of all of this stuff. And that was equal to just plain the hypotenuse. Okay, now the last thing that we'll look at in this section, or second last thing, is rationalizing the denominator. And that's really when you're dividing something. So if I say, or just for example, if I say I had 2/4, you look at that and you know I've got to simplify that to 1 over 2. And that's what you would just do as a matter of course, that you always want to simplify a fraction. Similarly, when you have a radical on the bottom of a fraction, like this, I need to get rid of that radical. It's just common. It's part of course is you're not supposed to have a radical on the bottom. So to get rid of a radical on the bottom, what we do is we rationalize the denominator. And we'll show how to do that in two cases. So first we'll look at a monomial. So if I just have one term on the bottom, the easiest way to get rid of that is to multiply the bottom by root 11 and multiply the top by root 11. Now you do that because on the bottom you're going to get root of 121, and root of 121 is those perfect numbers, so it comes out to just plain 11. And notice now I don't have a radical on the bottom. And then on top I just have to figure out what that is when you multiply. So the root 2 and the root 11, I can multiply those together. And then 3 times 1 out front would just be a 3. So my answer would be 3 root 22 over 11. I'm dying to divide that 11 into the 22, but one's inside a radical, the other one isn't, so I can't divide those. Now if you have a cube root, say like this one, when you have a cube root, what you want to do is multiply the top and the bottom so that you can get rid of this thing on the bottom. So when I'm multiplying this, I would say, okay, I only have 1 7, so let's multiply it by a couple more 7s. And then, oh, and this is cube root. And then there's 2 b's here. We can just multiply this by 1 b. And then when you multiply the bottom, notice what you'll have is you'll have the cube root of 7 times 7 times 7 times b times b times b. Right? B squared is, there's 2 b's there, plus this b from over there. So the cube root, when you have 3 7s, you can bring 1 out. If you have 3 b's, you can bring one of those out, and you'll have nothing left underneath the radical. And that's what you're looking for. But if you multiply the bottom by that, you also have to multiply the top by that. So 7 times 7 times b. So when you multiply, that'd be 49 times 3, which is about 157. That's still under the cube root sign. And then you'd have an a to the fourth and a b. Now the last thing you could do with this one, I don't know if you saw it or not, but right here, this is a to the fourth. If it's a cube root, there's more than 3 a's in there. So there's 4 of them. So I could bring 3 of those 8 a's out, and it'll have 1 a outside. And then I'll have the cube root of 157, just 1 a left and a b left, all over what I had originally for my denominator. Okay, so that would be simplified right to the end. Okay, so that's simplifying when you have a monomial on the bottom. If you have a binomial on the bottom, the trick that works every time to get rid of the radicals on the bottom is to multiply top and bottom by the conjugate of this. And the conjugate would be the same thing, root 5 and root 3, but this middle sign here has to change. So instead of a positive, this is going to be a negative. And both top and bottom, you have to make them identical. And then what you do is you FOIL the top, FOIL the bottom. Okay, well, I guess this top, there's just one term, so you just multiply it by that and multiply by that. And you can do that. I'll just do the bottom. So root 5 times root 5 would be root 25. Root 5 times negative root 3 would be a negative root 15. Root 3 times positive root 5 would be a positive root 15. See what's going to happen there? Root 3 times negative root 3 would be negative root 9. And like I said, you could do that stuff on the top. Now on the bottom, root 25 is 5. These two cancel. Square root of 9 is 3. So you actually have 5 take away 3 on the bottom, or that comes out to 2. And then you would deal with the stuff that you had on the top there. I just wanted to show you how to rationalize the bottom. Okay, last concept then for this section deals with rational exponents or fractional exponents. Here's some of the rules. So the rules say, okay, so the rules here say that if I have a base raised to a fractional exponent, that the denominator of that exponent becomes the index, and this exponent, or the 1, becomes the exponent of the a right there. So for example, if I had x to the 1/3, that would be equal to the cube root of x. Okay. Another rule, well, I guess it's basically the same thing. And the other thing to look at is if you have a negative exponent, you can flip it to the bottom and make it positive. Let's just try a couple questions. So if I have x to the 7/2 and I wanted to convert that to a fractional exponent, it would be x sorry, my pen's going funny here. So it would be x to the, I got to have a square root, and the bottom number becomes the index, which is a 2. Typically we wouldn't write that, but then the 7 becomes the exponent of the x. Now to simplify this, a square root means for every 2 x's in here I can bring 1 out. And there's actually, it looks like there's 3 pairs of x's in there, so I could bring an x to the cubed out, and then I'd be left with just 1 x inside. Okay, same thing with the 27 to the 4/3. It would be the cube root of 27 to the 4th. Okay, now it looks like there's 3 27s in there. Well, there's 4 actually. So if there's 3 of them, I can bring 1 outside. So there's 1 27 out, and then I'd be left with inside. I'd be left with just 1 27. But then the cube root of 27 is 3, right? So that would be 27 times 3, or I think that's equal to 81. So the answer to that question would be 81. Similar with this one, it's negative, so you'd have to flip it to the bottom. A couple more questions. Maybe I'll do this one here. It says the fifth root of the square root of 14. So there's 2 right in a row there. Let's change them to fractional exponents. So let's change the 14 first. So it'll be the fifth root of square root of 14 would be the same thing as 14 to the 1/2. Okay, now if that's the fifth root, then I could change this to 14. Okay, so 14 to the 1/2 raised to the 1/5, because an exponent out here would be 1, so I could have that as 1/5. And then power of a power, that would be equal to 14 to the exponent of 1/10. Okay, and you could do similar simplifications with both those questions as well. Last thing I guess we could do here is, like for this one, I could apply that 1/2 to each of those. So this a to the 7th would become a to the 7/2. So 7/2, that's a 7, over 25 to the 1/2. So I'm having to use my mouse with this. 25 to the 1/2, and then b, okay, minus 3 times the 1/2 would be minus 3/2. Minus 3/2. Okay, now doing a bit of simplification, a to the 7/2. I could write that as the square root of a to the 7th. Okay, that's that one, over 25 to the 1/2. That's the same thing as the square root of 25, which is just plain 5. And then this b to the minus 3/2, let's take that up to the top. And that'll be b to the positive 3/2 on the top. Okay, now a bit more simplifying here. Square root of a to the 7th, this is square root. There's 7 a's in there, so I could bring 6 of them out, and they'll become 3 outside, a cubed outside. And then this would be the square root of b cubed. B cubed all over 5. Oh, I forgot. I could bring 3 of those a's out, but I'd be stuck with 1 inside there. So there still has to be a square root of a there. Good. Now, square root of b cubed, I could simplify that one too. So that would be a cubed square root of a. This is square root, so if there's 2 in, I can bring 1 out. So that I could bring 1b out, and I'd be left with 1b inside, all over 5. And just to sort of clean it up, put things together, so I could write this as a cubed b. Those are all the things outside of the square root. And then inside the square root is 1a and 1b. Since they both have the same index, I can just put them under 1 square root, all over 5. Done. Okay, so try some questions from the textbook. Lots of practice with this helps out.